Good day, everyone, and welcome to this Lightbend webinar for December 3rd, 2020, titled The Reactive Principles, 8 Tenets for Building Cloud-Native Applications. My name is Oliver White, Chief Storyteller and MC at Lightbend. Joining us today is one of my favorite thinkers in the industry, Jonas Bonér. Jonas is the creator of Akka, co-founder and CTO of Lightbend, lead author of the Reactive Manifesto and the Reactive Principles, and an enthusiast of skiing, jazz, and strong Wi-Fi. While I introduce today's webinar, which should last the full hour, I would like to ask our audience a quick poll question. Have you visited the Reactive Foundation yet? Which you can find at reactive.foundation. So many people ask us at Lightbend if there is a right way to build a cloud-native application. Over the years, we have all certainly seen a lot of examples of what doesn't work well. So what have we learned? Well, we know that building applications for the cloud means embracing a radically different architecture than that of a traditional single machine monolith, requiring new tools, practices, and design patterns. The distributed nature of the cloud brings its own set of concerns. So if you're building cloud native, edge native, or IoT apps, this means building and running a distributed system on pretty much unreliable hardware and across highly unreliable networks. So today, Jonas will introduce these experiences from a high level as a set of 8 reactive principles designed to enable the implementation of cloud-native applications that are highly concurrent, distributed, performant, scalable, and resilient, while at the same time conserving resources when deploying, operating, and maintaining them. Thank you to all of you who voted. Some final remarks before we kick it off today. As always, today's webinar is made possible only by Lightbend's hundreds of happy customers that benefit from expert support, technology enhancements, Lightbend Academy, and observability and monitoring, such as our customer Cloud Imperium Games. They are looking for a senior microservices engineer to work on backend infrastructure services that assist with their release development and analytics pipelines. And they're using Akka, Scala, and Spark to do all of that. You can find out more by visiting lightbend.com and navigating to the About tab, where you'll find the Customer and Partner Careers section. This webinar is being recorded and will be made available for replay next week. So if you have to drop off a little bit early, you'll be able to see the end that way. If you have any questions for Jonas today, please feel free to add them to the GoToWebinar control panel under the Questions tab, and we'll see if we can get around to them in the Q&A part of today's session, although that will be rather short. And if you are an existing Lightbend subscriber, then you know that you can reach out directly to our expert engineers through the customer portal, where you can ask additional technical questions, what-ifs, how-tos, and best practices from our team. Okay, that's all from me. Jonas, it's wonderful to have you with us. Let's hand it over to you.
Thanks a lot, Oliver. Can you hear me all right?
Yeah, you're coming in pretty well. Folks, you can let us know in the chat if you're having any audio problems, and ideally, if you're using the web browser version of GoToWebinar, if you have audio or video problems, it's best to kind of restart and perhaps try to rejoin.
Okay. So I'm going to talk about the 8 reactive principles. I'll put a link up to a document that I started, and I've been having some great contributions from a lot of experts in distributed systems the last few months. We've been working on. We launched it a month ago or so, and I just want to say first that that document is really good practices based on experience from my experience and many others for building general distributed systems. And it's not specific to cloud. However, the cloud is a distributed system, so it naturally works excellent in the cloud. However, these principles are more, I'd say, more of a more general nature. So if you're building IoT applications, streaming applications, or any type of distributed systems, I think you will get some value from this. But to frame it a little bit in a little bit more practical, frame it into more practical context, I've decided to put it in the context of cloud native. So I'm going to start there and then move into the principles. So what does cloud native mean? A cloud native application, you can say, is like all native species in a way, has adapted over time and evolved into being sort of maximally efficient in the environment that it's supposed to run in, and in this case, the cloud. And it's a cloud native application really means that application needs to be distributed. That's the whole point of cloud native, having many of these applications running, many of these containers, and have the networking between them. It's a very different world that we will dive into more. But it's also a world that is empowering in a way. It can really give us a ton of more sort of tools to address hard problems like availability, like scalability, etc., right? So it's a very different world, but it's an interesting one and something that we should really take full advantage of. Sort of applications are sort of you can say that an application that's sort of meant to run in the cloud is one that follows the cloud operating model. And these you might disagree about these, but these are some of the sort of the principles of the operating model, or constraints rather than principles, that I found are very important and then affects the way we build systems. So the cloud operating model that I see it is that apps are limited in the ability to scale vertically on commodity hardware. And this leads us to distributed systems, to have many isolated autonomous services, what many call microservices. The cloud operating model also means that all inter-service communication takes place over unreliable networks. And that's a big one, because that means that all bets are off in a way. You can start adding the bets back in a way, but all bets are off when it comes to comparing it to running the system in a single on a single node, the classic monolith, where we have a lot more guarantees in terms of communication. It's also a fact that you need to always operate under the assumption that the underlying hardware can fail at any time, or it might not fail, but it might be restarted by the backend cloud provider or moved around. And all this affects, how you design systems to cope with that, to feel like that's something natural. It's also important that services are built to take to understand failure and to detect and manage failures in its peers, meaning the others it communicates with. And this includes partial failures or sort of gray failures. That's actually one of the hardest things in distributed systems, where not everything fails completely, but sort of a little bit. You might say. So steps in the chain might fail, or parts of a service might fail, and so the service might actually be able to sort of limp along in a way, but not provide full functionality. Sometimes actually better if the service just dies, so you can easily detect that and deal with it. Gray failures are usually very hard to manage, or to actually detect and manage, because they are partial. And the final or constraints is that strong consistency that we've been used to learn to love when it comes, in the monolith, when you have the one single relational database, it doesn't work as well in a distributed system, simply because transactions are extremely expensive across the network. You need to add some sort of XA, two-phase commit and these things. So it makes it difficult to create services that manage data, in available, performant, and scalable way. And then, what is the cloud native application? The way I define it is one that's designed to leverage these constraints, leverage the constraints of this cloud operating model. It's predictable, decoupled from infrastructure, it's right-sized, and all of these things, and it's supporting both development and operations, equally good, and it's it's a step into this world of microservices, you can say, where you decompose the system into this loosely coupled, independently operating services. So the question is then, why is cloud native infrastructure not enough? I mean, don't we have this? Is this not a solved problem with all the great cloud providers with Kubernetes and all of these things? Yeah, you might have seen this little comic strip fly by on Twitter or elsewhere. It's really telling. A lot of people think that it's like Kubernetes, or any cloud provider, you might say, but most of them actually run Kubernetes now. Is the only thing you need. As long as you just put your old stuff into containers, you're fine, and you can, because the Kubernetes will just manage it for you. It's actually not that easy. Kelsey Hightower summarized the problem, or actually the need for something more, very well in this tweet, where he said, and I quote, "There's a ton of effort attempting to modernize applications in the infrastructure layer, think Kubernetes and these other things, but without equal investment in the application layer, think frameworks and application service, we're only solving half of the problem." So we need to address this other half of the problem, and it's the fact that the infrastructure layer excels at managing and orchestrating and scaling and ensuring availability and all these good things of empty boxes of software. That's the containers. But managing these containers only gets you halfway there. That's only half of the problem, as Kelsey said. It's equally important what you put inside boxes, and also how you stitch them together into a single coherent system. You can't put old stuff into these boxes and expect new results. It goes. It's quite natural when you think about it. You need to put stuff in these boxes, meaning the containers, that are meant to run and designed for the cloud, that understands the constraints of distributed systems and tackle them head on. So I think we really need, for cloud native applications, we really need both a scalable and available infrastructure layer, Kubernetes, cloud providers, and all of these things, as well as a scalable and available application layer. And these two need to work in concert in order to really be able to build a complete, cohesive, full end-to-end application. That they can actually maintain the guarantees that you need end-to-end, from client down to data storage, all across, and also horizontally, across all these pods and Kubernetes, and Docker containers, across the whole life cycle of the application. So I really believe that we need to complement this infrastructure layer with something. And here I believe that reactive is really key. What is reactive? Reactive is really a different approach to thinking and designing and building reasoning about software systems, in particular distributed and highly concurrent system. It's really proven through years of experience. Way before I sort of started writing the Reactive Manifesto, and way before RxJava and other things came about. About 20 years old, I'd say. Some of the early reactive systems are Erlang and Pat Helen and Jim Gray's tandem computing, and it's really standing on the shoulders of giants here. It's just that today we need it more than ever. 20 years ago it was a niche. Now it's not a niche anymore. It's actually everyone needs to build on these solid principles, and they happen to work better than most places in the world of cloud, because it's really all about distributed systems, multi-core, being able to take a full advantage of the constraints and the new capabilities of the cloud. So I really believe that reactive applications are actually more efficient, more robust, more manageable, and adaptive and agile. And So what makes a real sort of an application reactive? You can argue that it's a reactive application addresses these challenges of distributed systems. You can argue that the most important thing is that it addresses the challenges of distributed systems directly in the abstractions, directly in the programming and data models, in the protocols, how the different components communicate, which is really, really key, and not tackling it as an afterthought, not as operational or infrastructure problems that sort of dealt with that layering complexity on top of each other and ending up with a sort of big ball of mud, but actually are honest and true about what distributed systems in the cloud is really all about, and encoding those constraints right into the programming model. But at least that's what I think is the most important takeaway from reactive application. It's honest about how reality works, really, and not try to hide it in a way. So the remainder of this talk, I'm going to introduce what I think are the 8 most important reactive principles, or the 8 most important principles to build applications for the cloud successfully. So that you should stay responsive, accept uncertainty, embrace failure, assert autonomy, tailor consistency, decouple time, decouple space, and handle dynamics. And if you want to read more, you should go to principles.reactive.foundation, where we have all of these written up in quite depth. But let's dive in. The first principle, stay responsive, means that you should always respond in a timely manner. Responsiveness matters. It matters a lot. It's really the face of your application, the face of your business, at least to your users, and it's really about the quality of service. It's sort of this bridge to your users, whatever they might be, humans or other systems, and that makes promises to your users. And stay responsive is all about making sure that you keep these promises, keep the SLAs needed. So it's really sort of the cornerstone, I think, about usability, really, and utility and value. And it's quite easy to stay responsive during blue sky scenarios, when everything's going great, everything going as planned. And that's often what we test for, the sort of happy path. But it's actually way more important to test for the sad path, or when things start to fail, because it's equally important to stay responsive in the face of failure. When you have communication outages and unpredictable workflows, when you sort of get slashed on it, as we used to say when I started building systems about 20 years ago, when there is a spike, essentially, and that you couldn't plan for, some which is usually a good thing, where you get more users and traffic to your site if you're real data application or web applications, but unless you can manage that spike in a good way and not fall over, it's actually it won't help you. So it's really about being able to stay responsive in the face of unexpected failures, it's to you, in a way, from the perspective of your users, it really doesn't matter if your system is correct, unless it can provide functionality within a reasonable time frame. If that makes sense, whatever that time frame is, it's really up to the application, but it needs to provide value in some sort of timely manner, I think. And in the worst case, if you actually have to fail, or if things do fail, then respond with an error message, or provide some sort of degraded but still useful level of service. In the essence, the essence of graceful degradation is really to have a plan how to manage overload and to manage, when things starting to go south. I really enjoy this quote by Mitch Hedberg. He's the late comedian, and he said that an escalator can never break; it can only become stairs. You should never see an escalator temporarily out of order sign, just an escalator temporarily stairs. Sorry for the convenience. So it's really about being able to back off and provide still a useful subset of value without completely failing. Sometimes it's, of course, might be better to fail completely, and at least for a subset of your users, to provide full functionality for the other half of the user, so to speak. It's all depends on the type of use cases, but having some way of managing overload and partial failures is usually really useful. So of course there's a lot more to say about that, but in a way responsiveness is really everywhere. It really affects almost everything in your application. It's sort of elusive in a way because it's sort of really everywhere and nowhere in a way. But it's really the foundation that all of the other helps to maintain in a way. Because I say it's really the face of your application, and without that you simply are not providing value. And then why are we even building the application in the first place? The second principle is accept uncertainty. Build reliability despite unreliable foundations. And as soon as you exit the boundary of your service in a distributed system, you sort of enter this wild ocean of non-determinism. And that is the world of distributed systems. It is really the world where systems fail in the most spectacular ways, the most intricate ways, the really, really weird ways, where information gets lost and reordered and garbled, sort of, and corrupted, and we're failure detection. Just the act of understanding if the peer you're talking to is down, or if it's just being a bit slow today, it's a guessing game. It's really just a numbers game. It's how likely is it that it's down right now, and how likely is it that it will be just back next second. And this world might sound terrifying, and it in a way is, but it's all the world. It's also the world that gives us solutions for a lot of these hard problems, like resilience, like elasticity, like isolation between services and microservices, to etc. So sorry, I don't know why it says to do here. Anyway, I just talked to. I think I opened an old set of these slides, but I think it's fine. One of the key
maybe that's a sort of question that can never be solved, and it's permanent to do.
The present that we perceive is really relative and subjective, and one of the fundamental problems is that we don't have a really good way of doing consistent and reliable shared memory across the network. It's easy, sort of easy in quotes, but it's sort of reasonably easy on a single node. But as soon as you move to the distributed system, it's really a lot more complicated, because we can't wait indefinitely for information, for knowledge, for directions to make a decision. And if we can't wait indefinitely, on the network where messages might get dropped or where you have a full network disconnect, that means that we can't sort of really so all bets are off, really. And it's extremely important that, as in reality, I have to say, as in real life, the present and now is really subjective. because some other service is experiencing a different now. Even if you use timestamps, they are likely to be not fully reliable, and there's still latency, between information between services, because information travels at the speed of light, and that puts a hard limit on speed of information. And that's really a reality in systems today. It might sound like some esoteric physics phenomena. Why should I care about that? But if you're building global systems or having users on other continents, is really a hard limit that you need to take into account. And it's the fact that information is always from the past. Everything. If you think about it, in reality, everything is always from the past. It's at least everything that we observe. When you observe something, some effect or some event, it has already happened. Sometimes actually quite some time ago. So in a way, we're sort of always looking into the past, and the present and now it is always subjective. It's always in the eye of the beholder. It's always relative in a way. And this has a lot of implications. That means that we can't always trust, for example, time, as measured by wall clock time, and timestamps representing the latest wall clock time that we send around. And we can't always trust order. The causality in the systems might not even exist. Because it might be hard to understand causality when you have multiple paths to across the system. And accepting this uncertainty, is extremely important. And instead having strategies how to cope with this uncertainty. Things like relying on logical clocks, such as vector clocks, for example, or if possible, or if needed, rather than possible, use eventual consistency. So like CRDTs and completely replicated data types, or using a NoSQL database that provides you eventual consistency guarantees. Because all of these weakened guarantees that might sound like a bad thing actually increases the headroom in a way for what we can do, for what's possible when it comes to availability and scale. That is everything is trade-offs in our world, and it's really about managing these trade-offs in the optimal way. We need to make sure that our communication protocols are associative, meaning that they're batch insensitive, that they are commutative, meaning that order doesn't matter, and that they are idempotent. That means that duplication of retransmissions is actually fine, because that the receiver can always handle them. We really need to model and manage uncertainty directly in the application architecture, directly in the application design. And as Pat Helen said, in a system which can't count on distributed transactions, the management of uncertainty must be implemented in the business logic. And transactions are actually often a poor option, which I'll talk more about later. So what it really comes down to is having good principles to manage the space in between services, because that's where all the hard things will happen. And not try to hide the constraints, but make it explicit, making it first class in the application design, and especially making the network and constraints of the network first class in the application design. It's really about looking at how reality actually works and exploit that in our design. Use that to our advantage. Think about how would we solve a problem in the real world, moving away from computers, which is sometimes a world that sometimes we try to cut corners too much in a way, and instead use this mapping to reality to our advantage, and try to encode reality more in our applications, I have to say. The third principle is embrace failure. Expect things to go wrong and design for resilience. A couple of different strategies for this. it might be, you know, that this one that you sort of just freak out or run for cover, or just expect that everything is fine, everything will just go as you want eventually. You know, neither of these strategies are sustainable and or particularly healthy, I have to say. Instead, we need to manage failure and not trying to find ways of avoiding it, because there's really no way of avoiding it. Failure is really inevitable. It is, and the way I view it is that it's not just inevitable, it's actually something natural. It's not something we like, it's not something we enjoy, but it's natural nevertheless. In a way, you know, it's sort of ironic that a lot of programming languages or frameworks call failures exceptions, because there's really nothing exceptional about failure. The way I view it is that failure is just a natural state in the application's lifecycle. You have start, you have stop, perhaps, you have pause, you have resume, and then you have fail. And if you look at it like that, it's a natural state in the application's lifecycle, just as part of the application state machine. Then if you end up in the failed state, there's nothing to worry about, because you know exactly how to get back, just as you know exactly how to get back from resume onto running, for example. So it's extremely important that we build systems that are designed for failure. They're designed to manage failure instead of trying at all costs to avoid it. And you know, resilience, the way I view it, is really by design. It's nothing that you can bolt on afterwards. It really needs to be part of the design from day one. This is really sort of really powerfully illustrated by this photo. I think it's a photo from a home in Gilchrist in Texas. It was sort of designed to resist floodwaters, and it was one of the few, as you can see, homes that survived Hurricane Ike in 2008. It was a home that was built with failure in mind, with resilience in mind. It was designed to stand up against failures. And it's also important to understand that, as Sidney Dekker says, accidents, failures, they come from relationships, not broken parts. As you know, that it's usually in the boundaries between services, in handoffs between services, on the edges of systems that failures start to compound. So it's extremely important to look at the systems holistically, and to do good. You know, when failure happens, take the time to do postmortems and really understand how your components interact, because it's usually a really small failure can sometimes escalate and take down the whole system, even though in isolation that little small failure doesn't look so bad in a way. A couple of principles that we'll talk about later is decoupling in space and decoupling in time, but I'm going to reference them here because I really believe that they help in building resilient systems extremely well. Decoupling in space allows failure to be kept inside designated failure zones, a way to contain failures and avoiding them to leak and causing, as I talked about, cascading failures, sometimes taking down the whole system. The key here is to have a good way of doing compartmentalization, and that is usually what we refer to as bulkheads, a term that we stole from the ship construction industry. It's also extremely important to be able to decouple the system or the components in time, because that enables all other components to reliably detect and handle failures, even when they can't be explicitly communicated, which is also a very important part of the story. So requirements for a sane failure model, in my opinion, is that failures, they first need to be contained to avoid cascading failures, as talked about, but they also need to be reified, sort of, wrapped up, sort of, and as values, because values are stable, immutable, things that you can trust. So that they're really good to base future reasoning upon. Once you have wrapped up the failure as a value, you should have a way of signaling them asynchronously to other components, other systems, sometimes either, other nodes, and where they can be observed. Sometimes by one, sometimes by many. It can sometimes be beneficial to have more than one subscribing on the failures, but sometimes it's just one. And the important thing here by this signaling them, ideally across the network, means that they can be managed outside of the failed context. It might be the whole node is going down, but the failure was signaled to another healthy node. That node can now take action and manage the failure by restarting him on the same node when the node comes back up, restarting the service on another node, perhaps, or the same node that the sort of supervisor is running on. I also believe that sometimes let it crash is simply the best way. Fail fast to avoid the system to sort of cripple along, being crippled and sort of limp along in some sort of half working state. Sometimes better to just fail, and having a way. And then if you then have a way of notifying others about the failure, you have a really good foundation to build self-healing systems. I have a lot of experience doing that in using the actor model, for example, and a lot of things that I learned from Erlang and Joe Armstrong that we sort of encoded into Akka. But there are other systems as well that adopt this model, like Elixir, for example. Vlingo is another one on the JVM. There are many sort of actor-style systems, and most of them implement this way with supervisor hierarchies and let it crash mechanics. But it's not really tied to the actor model things. These are general ideas that can apply to almost anything. The next principle is assert autonomy. Design components that can act independently and interact collaboratively. So, but first, what does autonomy really mean? When I looked it up some time ago, so the definition I got was that it means to be self-governed, to being able to act on your own values and your own interests, so act in self-interest, and being sort of in control of your own destiny in a way. And this can be achieved by defining clear component boundaries and encoding that in clear protocols. Understanding who owns what data, how these owners make things available, and also by designing them that each party is afforded the necessary degree of freedom to make his own decisions and not being just held accountable by others. Not just implementing this sort of command and control paradigm, but having a more event-driven architecture is often helpful, where components subscribe to the events it wants, it's interested in, and can choose himself to act upon these events that fly by. While command and control usually leads to more coupled systems. Because there's always someone waiting for you to give your answer now. Usually a combination of command and control and more demand-driven is helpful in most systems. But I personally tend to lean more towards sort of push event-based type of systems where components act at their own will when events fly by, so to speak. We need to craft sort of safe autonomous islands of strong consistency and determinism. And it's really a way to bring some sanity in this wild ocean of non-determinism that we talked about in the past. Entering a distributed systems really means that you're introducing a lot of non-determinism. but having ways to craft these islands where we sort of can live happily under the illusion that time is absolute, the illusion that you're in control of time, that there is a single present and then the world is deterministic, can be really helpful, even though it's sort of only an illusion, but it works within this safe island of the component boundary, so to speak. Shared mutable state, sort of update in place, can be problematic. It's because it often leads to wait time. Simply, it leads to contention that leads to wait time, and also leads to coordination, need for coordination, and as a result of that, we often get reduced availability and scalability. It's extremely important, I think, that we need to be able to contain mutable state. I'm not saying that mutable state is bad. Mutable state can be extremely useful. It's actually very intuitive for people that sort of being taught C and C++ in school and are used to this world of updating place. Also used to see SQL databases and things like that. So it often feels quite natural to think in terms of that for us as programmers. So I don't think we should stay away from that, but it's extremely important that mutable state is contained. That we contain it within these sort of safe islands of the service. And that mutable state is made non-observable to the rest of the world. We can go about and use it as much as we want, as long as it doesn't leak, as long as it doesn't escape the component boundary, as long as it's fully contained in this safe haven, and only used for local computations. And when we're done with our processing, when we ended up with some sort of outcome, some sort of result, or whatever we try to do, and we're ready to tell the world about our results, then we can wrap that result up as a fact, as an immutable value that we can then communicate to the outside world. And good tools for this is using domain-driven design with bounded context, for example. Event sourcing is another great one with CKRs and so on. I don't have time to go into that, but let's see. I'm just going to leave it at that so we don't run out of time. The next principle is tailored consistency, individualized consistency per component to balance availability and performance. It's extremely important that we don't sort of carry around more guarantees than we actually need, because every guarantee has a cost. Every guarantee you have to pay the price for that. So it's often better to start with as little guarantees as possible, and then add guarantees as we need them, instead of just out of habit use, for example, strong consistency, because we're used to that. We're used to just using a SQL database that provides strong consistency. We're used to building systems using the monolith, where strong consistency is quite cheap. But in the world of the cloud, in the world of distributed systems, strong consistency is extremely expensive. It's not saying that it's not useful, not saying it's not good. It's great, but it's really the wrong default, because strong consistency is just too brittle. It's really hard to make it available. As Pat Helen said, two-phase commit, meaning sort of transactions across the network, is the anti-availability protocol. And also that he said that in general, application developers simply can't implement large-scale distributed applications using distributed transactions. It's from his great paper, Life Beyond Distributed Transactions, that I really encourage you to read. What does this mean? It means that we have to rely on eventual consistency. But we shouldn't really be surprised, because as I talked about earlier, we need in the world of distributed systems, I believe that we can have a lot to gain by mapping how the world works into our system. And the world is eventually consistent. There's really no thing that's strong consistency between multiple parties. I think humans, or when we interact naturally, it's all eventually consistent. So I communicate with you, and there's latency, and then you might do some sort of reasoning and thinking, does this make sense? And if so, create some sort of fact about that. It's really all eventually consistent. So I think we shouldn't fight reality. Instead, we should embrace it. And one way that I view systems in general, these type of systems, is that it's really a never-ending stream towards convergence. We're always in the process of convergence, but we never ever reach the state of full convergence. In a way, the system is in constant motion. It's in constant state of change. It's always trying to catch up towards full convergence, but it's never ever going to get there on a final, complete basis. Again, there really is no now. Everything is relative. Everyone's playing catch up with everyone else, and so on. And one thing that's really helpful is to think in terms of consistency boundaries. To think in terms of these small islands of strong consistency in a river of constant change and uncertainty. These small islands where we can bring sanity back, where life is easier, so to speak, and so where we can, and one sort of really good way of managing the world without transactions, I think, is to do what Grace Hopper once said, that it's easier to ask for forgiveness than it is to get permission. So if we can coordinate with others in sort of strongly consistent fashion and be certain about something sort of definitely, then what do we do? I mean, in the real world, what do? We usually take an educated guess. Sort of we take a bet that some sort of condition will hold, and if we're wrong, what do? We apologize, and we perform some sort of compensating action. It really matches how we humans collaborate with each other all the time, I think, and I think we should bring that back into systems. Having good protocol to manage this really helps. Examples from the real world about this is, for example, airlines. I mean, most people that have been flying a lot know that they sometimes can overbook flights, and then they try to bribe themselves out of the problem by issuing vouchers. So guessing that it won't be fully booked, apologizing, and then compensating people, really. And ATMs work the same. They allow you to withdraw money even though you have a network disconnect, if you can't talk back to mainframe where the source of truth is. But then we'll later charge your account, sometimes with interest, actually. Again, guess, apologize, compensate. And Pat Hellenser, once again, has defined in a really nice framework, I think, or conceptual model how to think about systems like this, where you have inside data. That's our current present. That's the state we have in our system. And then you have outside data. That's what he calls blast from the past. That's the facts that are arriving into our system. That we always sort of looking into the past in a way, always trying to catch up. And finally, we have between services commands flying. That's what he calls almost, poetically, hope for the future. Someone asks someone else to do something through the command. So you have state, that's your internal state, that's your current presence, the only thing you can really trust. Then you have the blast from the past, facts arriving, and then finally you have commands coming, so requests, please do this. That's a model that's really been helping me think about these type of systems. And within this safe consistency boundary, you actually can have strong consistency. I just want to emphasize that. But it's really important then that this consistency boundary and ensure that the component lives and dies and is restarted in isolation, that there really is no way of doing that partially. So if you so you can have because having an atomic view of the state and having each service own its data exclusively is extremely important here. Because between the consistency boundaries, it's still a zoo. But again, it is actually this zoo, this craziness, and this all bets are off that gives us tools for availability and scalability, because it lifts the ceiling on what's possible. We need systems that are decoupled in space and time, as I've sort of referenced a little bit earlier. That's really a way to manage the space in between, manage this zoo, to decouple things. And we need to decouple things in time, or services in time. That's really what gives us concurrency. That allows us to put an asynchronous boundary between components and gives us this loose coupling that we really need. It's also extremely important to be able to decouple the components in space, because that's what gives us distribution across cores, across nodes, across containers, across data centers, and it really what gives us mobility in systems, which eventually gives us, things like replication and things that leads to resilience, as we talked about in the past. It's also extremely important then, as I said, it's really important to decouple the systems in time. Process asynchronously to avoid coordination and waiting. That's principle 7 or 6, I think we're up to now. As Bob Monkhouse once said, silence is not only golden, it's seldom misquoted. It's sort of a funny quote, but I really believe it's really, really true, because if you never communicate, there's really nothing to coordinate. There's really nothing to wait for. There's really nothing that you have to make consistent. If you don't, all problems in distributed system comes from the need to coordinate and communicate with others. So if we can cut that down to a minimum, remove all needless coordination and communication, we're actually in a lot better place. Sometimes it's not needed, of course. All systems need to coordinate and communicate in some way, but being a bit cautious about it can really, really help. And it's also really important to reduce temporal coupling. It's sort of one way of implementing this, and temporal decoupling really helps breaking down, the need to have components available at the same time to actually do work. When multiple components synchronously exchange messages, it sort of presumes availability and reachability of these components at all time. Actually, not at all time, but during the exchange, during the communication session, so to speak. As we talked about, this is an extremely fragile assumption in the world of distributed systems, because we simply can't ensure availability and even reachability of all components at all times. Components will come and go. They will be by the back end sometimes restarted and moved around just because it's more efficient. So it's not always due to failure. So having techniques to manage this is extremely important, and this includes things like traditional things like having durable message queues, having append-only journals, and using publish, subscribe with topics, often then with some sort of retention policy, so you can replay messages if needed, if the system fails. All these are really important things, and also with temporal decoupling, it really sort of gives the caller in the chain sort of option to perform other work asynchronously, rather than just be blocked waiting for something to happen, as you can see in this little illustration here. It's really about making a really efficient use of resources and to minimize contention, because contention is really the biggest scalability killer in a system. It sort of holds the caller hostage in a way until the callee has finished doing whatever he wants. And that's extremely wasteful. Instead of freeing up resources and allow the caller to go off and do something else while he's waiting, and then instead being notified through some sort of event using futures or promises or async await or coroutines. There are many different techniques as a way to orchestrate these type of callbacks. But it's better to just register the callback and then go off and do something else. Say, notify me later whenever you're done, instead of blocking so needlessly, because this really kills both availability and throughput, as I said. So if we're going to sort of dive down just a little bit here, we have essentially two things. First we have contention. That's sort of the waiting on shared resources, and that is well described by Amdahl's law. You might have heard Amdahl's law. It's really Amdahl's law really explains sort of the effect that contention has on a parallel system. That contention can give us diminishing returns, as you can see in this dotted line here. So when we add more cores or more nodes, that's the horizontal axis here, we're not getting a linear payoff in a way. But the more cores, we're getting smaller and smaller return depending on how many cores we're adding or nodes we're adding. But that's only sort of half of the truth, because it's equally important to consider coherency. And coherency is actually the work that needs to be done to coordinate. It is the delay for data to become consistent. And that's described by Günther's universal scalability law. And when you add coherency into the mix, this coordination that I talked about, it's actually the case that sometimes it can give negative results. So incoherence, as it's called. When you start adding more nodes, you can actually make things worse, because the work of communicating and coordinating all of this across all of these extra nodes just takes up more of your resources than doing the actual work in a way. So it's really the weakest link in the chain that matters here, and it's extremely important to through good tools and good analysis, understanding sort of the effect of all stages in your workflow. So you don't have one stage or one processing or one component in the workflow that sort of kills it for everyone else in a way. So it really needs to be async and non-blocking all the way down. We also need to decouple systems in space. That means we're creating flexibility by embracing the network. I've talked a lot about this in the past, but I think it's so important. It's really what we really need to do is sort of embrace the network and make it first class in the programming model. It's really about embracing the constraints of realities I talked about, and not trying to hide it like we've done so much in the past. If you look at the history of computer science, we've done this. We've been failing at this over and over again. Through EGBs, Corba, DCOM, and all went through the work of adding the leaky abstraction that sort of pretends that the network is not there. That is just it looks beautiful when you look at it from the outside. You can just communicate with other components using some sort of local abstraction. But the problem is that it often leaks. It leaks so much that it becomes really, really hard to use. Not in the happy path, but when things start to fail. Because if you hide things and not making them explicit, then if things really start to go wrong, not through party failures, message loss, and and all of these things that you can end up with, grade failures, then you really have no way of managing that, because you have this shiny, nice abstraction of localness that you can't penetrate. All these ways of managing that is hidden from you. It's often better to make distribution in the network first class. For example, as done in the actor model, it's one of the reasons why I love actors, because it's really all about making the distribution and concurrency first class in the program model. And one thing that leads to is to what we call location transparency. And location transparency means that we have one abstraction for communication across all dimensions of scale. I mean, regardless how the system is deployed or which topology it has, because that might change. The beauty of it is that it should change if you run it in the cloud. Containers might move around. That means that services should be able to move around. And if you have one programming model with unified semantics, then you haven't hard coded into the system how the topology should look. It's instead of, as we've been used to do in the past, rely on different tools and different semantics for each layer, for each level of scale. You can say you have, for example, callbacks for a single core. You have threads and locks across cores, and you might have some sort of message queue across nodes and across data centers. Instead, async messaging, for example, can be a unified abstraction here. That makes distribution and network and communication the same across all these levels, all these dimensions of scale, so to speak. Working with the same semantics, sort of anyway, because latency might increase. So it's not exactly the same, but it's close. That means that the runtime can allow you to talk to a remote service a lot, and then have the liberty of moving that service closer to the application, to the actual context where it's being used. Optimize things by moving the services around to make most use of the, or make things most efficiently globally, so to speak. The final principle is handle dynamics, continuously adapt to varying demand and resources. It's extremely important that we are able to apply back pressure all the way. Have some sort of way of managing flow control, and that should be encoded in the protocol. Say a lot of these things really leverage good protocol design, and the key here is that a fast producer should never overwhelm a slow consumer. Everyone needs to participate. As you can see, this little illustrative video here. It's really a system that is really lacking flow control or back pressure. And this is a reason, for example, why we created the Reactive Streams protocol as a way to standardize across not just services using the same library, but even across libraries, across systems, to sort of negotiate the best rate of how events should flow in the system, to make sure that we do it as fast as possible, but never overwhelm the stages downstream, so to speak. See, this is actually, as I said, I'm running an old slide deck here. So that's all I had, actually. I'm sure it's a lot to take in. If you want to dive down into some more details, you should go to the principles.reactive.foundation, and I don't know if there are any questions.
All right, thank you so much, Jonas. I'm glad that the fish catching GIF at the end worked, and that's a great illustration of what you're talking about. I think we're gonna end now. There were a couple questions that I believe were answered during a later part in your presentation.
Oh, here we go. Sorry, I didn't have any sound. Sorry.
Oh, okay. Can you hear me?
So, yeah. Could you repeat?
Okay.
If you asked the question, could you repeat it?
I was going to say that I believe the questions that we had were actually answered later in your presentation, so
Okay.
I think we're good to go. And this was we went a little bit long today, so thanks to the audience for sticking with us. Again, visit principles.reactive.foundation to see the full description of what Jonas presented today. And you'll also notice that there were a lot of contributing authors, many of whom you may know. And it's really a wonderful document, and I wish that you can go there and find some clarity. So Jonas, thanks so much. And do you have any final comments for our audience today?
I don't. Actually, as I said, I mean, I'm bummed that I used like some 3-4 week old slide deck here. I'll make the slides available, the latest ones, and that actually has some more links and other things in them.
All right.
I hope it was still useful.
I think people were happy with what they saw. All right, folks. Well, that's all. If you have any questions for us, you can email me directly at oliver@lightbend.com, and I'll make sure you can find the right person to talk to. So thanks for joining us, and have a wonderful day and weekend.
Thanks, everyone.